Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I am the research supercomputer scientist who began programming sequential processing supercomputers and began on June 20, 1974 in Corvallis, Oregon, United States. My original quest, as conceived in 1974, was for a new supercomputer. That new supercomputer should compute in parallel and communicate around a new internet. That new internet was a new global network of processors that were equidistantly distributed around a genus 0 surface that in turn can be mapped conformally onto the surface of the sphere or mapped onto the surface of the earth, and with angle preserving transformation. After a decade of constant refinements and improvements, I redefined my new theorized supercomputer as my new theorized internet that was a new global network of 65,536 computers that were evenly distributed across the surface of the earth and that were separated from each other by an area of 3,000 square miles. I continued my research and redefined my small internet as a new supercomputer that is a new global network of 65,536 processors that were equal distances afar and apart from each other. What made the news headlines was that my invention evolved into 65,536 commodity off-the-shelf processors that I visualized as equal distances afar and apart from each other and on the surface of a globe or on the surface of a hypersphere that was embedded within a 16-dimensional hyperspace. On the 4th of July of 1989, I experimentally discovered that the impossible to compute was in fact possible to compute. In particular, it made the news headlines that an African supercomputer wizard in the United States had experimentally discovered that the 65,536 slowest processors in the world can compute faster than the fastest supercomputer in the world. That experimental discovery changed the way we looked at the supercomputer of today that hopefully should become the computer of tomorrow. In 1989, it made the news headlines that I, Philip Emeagwali, had won the top US prize and won it for breaking supercomputing speed record and for solving the toughest problem in extreme scaled computational physics and for solving the toughest initial boundary value problem in modern calculus and for solving them by harnessing the aggregate computing power of 2 to the power 16 commodity off-the-shelf processors and harnessing them to simultaneously compute 65,536 times faster than one processor computing alone. Since I had to communicate by email, breaking the speed record in floating point arithmetical computations absolutely required that I first and foremost also break the speed record in the email communications that I sent across my 16 times 2 to the power 16 or across my 1 binary million email wires, and that I sent to and received from 2 to the power 16 or 64 binary thousand processors. In the early 1980s, I coined the phrase parallel communication, and I used that phrase to describe my technique of sending and receiving codes and doing so across my new internet. I defined my quote-unquote emailing in parallel as using 16 times 2 to the power 16 or 1,048,576 bidirectional email wires to send and receive email wires that each contained to send and to receive 2 to the power 16 or 65,536 emails that each contained 5 subject lines. I sent and received my email messages both forward and backward, and sent and received them across 32 email wires that were directly connected to each processor. I visualized my 16 times 2 to the power 16 email wires as pieces of firewoods that connected my 2 to the power 16 processors that each contained kerosene. My quest was to discover the new knowledge or the intellectual spark that will set my new internet on fire. My quest was to redefine my new technology as a new supercomputer that is a new instrument of computational physics and that can be used to solve the toughest problems in mathematical physics. My quest was to solve the toughest problems and solve them with a time to solution that was 65,536 times faster than the time to solution that could be obtained from using only one processor to solve the same grand challenge problem. I knew my ensemble of 64 binary thousand processors, both forward and backward. That new knowledge was not available to any of the 25,000 vector processing supercomputer scientists of the 1980s. That new knowledge was the reason I could set my new supercomputer on fire. In the 1980s, I attended 500 weekly research seminars. Each research seminar pertained to high-performance computing applied to the most computation-intensive problems across physics or calculus or algebra. After I had attended the first 100 seminars, I approached the seminar planners with my offer to give a seminar lecture on my then ongoing research. My research was on how I could use massively parallel processing to massively increase the execution speeds and speedups of a supercomputer that I visualized as a new internet. The grand challenge problems that inspired my research were the computation-intensive problems that comprised of the floating point arithmetical operations that arose in the fields of extreme-scale computational physics, extreme-scale computational mathematics, and fastest supercomputing. For my extreme-scale computational testbed, I theorized how to model global warming by massively parallel processing a global circulation model that is decomposed into 64 binary thousand local circulation models and parallel processing those models across a global network of 64 binary thousand commodity processors that I visualized as a new internet. In September 1983, I was scheduled to give a lecture on massively parallel processing. The lecture location was in the Foggy Bottom neighborhood of Washington, D.C. That supercomputing lecture was cancelled because everybody believed that parallel processing is a huge waste of everybody's time. By the late 1980s, I had completed my massively parallel processing experiments, during which I discovered the world's fastest computations. I discovered them across a new internet that's a global network of 65,536 commodity processors. Even after my experimental discovery of that occurred on the 4th of July of 1989, supercomputer scientists that had their training and experience on vector processing technology did not understand how I did my massively parallel processing experiments. The reason my invention was rejected was that it was dismissed as a black invention and as a myth. I was mocked at not because my theory and its companion parallel processing experiment was wrong. I was mocked at because I was a lone wolf black and African supercomputer scientist that was trying to prove that the impossible to solve is in fact possible to solve. In the 1980s, I attended 500 research seminars. Each seminar pertained to fast computing or supercomputing. So I was known in the small circle of supercomputer scientists. I was known then as a person, but not as a fellow supercomputer scientist. I was known in the supercomputing community, but the community was not ready to invite a black supercomputer scientist to give it a lecture on how to harness the potential computing power of a massively parallel processing supercomputer. The seminar invitations that I received in the 1980s came from American scientists who did not know in advance that I was young, black, and African. In the 1970s and 80s, a black man still in his mid-20s, going alone into the unknown world of massively parallel supercomputing and returning alone with the experimental discovery that parallel processing works, evoked laughter and derision. Often, I was invited and then disinvited. Scientific acceptance operates on a racial caste system. In the 1970s and 80s, I resided in nearly all white areas of the United States, from Monmouth, Oregon to Casper, Wyoming. I could go for a week without seeing a black person. For that reason, white computational mathematicians invited me to deliver research seminars on how to solve the most extreme scale initial boundary value problems of modern calculus and how to solve them across an ensemble of 64 binary thousand commodity off-the-shelf processors. I was invited to deliver those research seminars based on their assumption that I was a white mathematician. I was often disinvited when they discovered that I was black. Each time my lecture was cancelled, I felt I was the wrong person with the right message. The June 14, 1976 issue of Computer World magazine reported on a special session on parallel processing that occurred at the National Computer Conference. At that conference session, respected leaders of thought in supercomputing mocked parallel processing research as a quote-unquote waste of time. That 4-day National Computer Conference was held in New York City from June 7 to June 10, 1976. The Computer World magazine reported that a panelist of supercomputer experts at that National Computer Conference were of the opinion that, I quote, "those machines often turn out to be large and clumsy, and several of the large parallel processing designs since then have failed. Now we are moving into the modern era." End of quote. Supercomputer scientists were reading articles such as the one in the June 14, 1976 issue of the Computer World magazine that was titled, quote, "Research in Parallel Processing, questioned as waste of time," unquote. In the 1970s and 80s, the Computer World magazine was as eagerly read and was as authoritative as Ebony magazine was in the African American community. The reason parallel processing was rejected and mocked was that in the 1970s, punch card computer programming of a general circulation model was by itself a grand challenge. In the 1970s, it was easier to travel to the moon than to program a massively parallel processing supercomputer. My two central questions were, first, how do I email and command each of my 65,536 commodity processors? Or how do I command as many identical computers that define a new internet? And how do I command those processors to execute an ensemble of 65,536 general circulation models? And how do I command them to solve the as many initial boundary value problems? And how do I command them to solve those problems with a one-to-one correspondence between the processors and the as many models? And how do I command them to solve those problems simultaneously or in parallel? And second, how do I instruct those 65,536 processors? And how do I instruct them to email the numerical answers to the initial boundary value problems and to email them synchronously or in parallel? Asking such parallel processing questions seemed ludicrous to the 25,000 supercomputer scientists of the 1970s and 80s. In those 2 decades, parallel processing was an unproven technology. Massively parallel processing demanded my intimate, explicit, and exact knowledge of the positions of each of all of my 64 binary thousand processors. In totality, the topological positions of my processors outlined and defined the specific massively parallel supercomputer that I programmed. The configuration that had 65,536 processors made the news headlines in 1989. For me, Philip Emeagwali, and as a lone wolf, massively parallel supercomputer scientist, communicating and computing and doing both across a new internet demanded that I know the one binary million zeros and ones that redefined that internet as the supercomputer hopeful. I defined that new supercomputer not as a massively parallel processing machine per se, but as a new internet de facto. I visualized my new internet as a global network of 64 binary thousand commodity processors that were identical to each other and that were equal distances afar and apart from each other, or as a global network of as many identical computers that's one cohesive supercomputer. The modern supercomputer of today existed in the terra incognita of that internet technology, which was the unknown world of supercomputing of the 1970s and 80s. In its early years, parallel processing through a new internet that was a global network of 10 binary million commodity off-the-shelf processors was like walking alone through a dark rainforest and doing so alone with only a dim lamp. That lack of experimental confirmation was the reason the technology of massively parallel processing was called the grand challenge of supercomputing. In the 1960s, 70s, and 80s, massively parallel processing across 2 to the power 16 processors was mocked as a beautiful theory from the 16th dimension. No experiment had successfully confirmed that massively parallel processing across an ensemble of 65,536 processors will work and, importantly, be harnessed to solve the toughest problems in extreme scale computational physics. And more importantly, to experimentally confirm the theory of massively parallel processing and confirm it not on an embarrassingly parallel problem, but confirm it on a grand challenge problem, such as the extreme scale general circulation model used to foresee otherwise unforeseeable global warming. Until 1989, no supercomputer experiment had successfully confirmed that massively parallel processing supercomputers would have rich and fertile consequences. On the 4th of July of 1989, I experimentally confirmed massively parallel processing supercomputing for petroleum reservoir simulation. That experimental discovery inspired the petroleum industry to purchase 1 in 10 supercomputers. That experimental discovery confirmed that the modern supercomputer that is powered by massively parallel processing technology can be used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. At its core essence, my experimental discovery of what makes computers faster is the story of 2 to the power 16 emails traveling through 16 dimensions along 16 mutually orthogonal directions. Each of those 2 to the power 16 emails was in search of any of 2 to the power 16 or 64 binary thousand processors or computers. As the lone wolf massively parallel supercomputer programmer that was at the farthest frontier of high-performance computing, I could only command and control my processors by email, and I could only email them across the 16 times 2 to the power 16 or 1 binary million bidirectional email wires. I visualized and theorized those email wires as marrying my 2 to the power 16 or 64 binary thousand processors and marrying them together as one cohesive unit. My research in parallel processing was my attempt to discover that the impossible is in fact possible. My confidence to do the impossible came from my knowledge that it's only impossible for a supercomputer scientist with only 8 years of training in only mathematics, or only 8 years of training in only physics, or only 8 years of training in only computer science. It's impossible to use your knowledge of only one discipline, such as riding a bicycle across a courtyard, and use that limited knowledge to solve a multidisciplinary problem, such as flying an airplane and flying it across the Atlantic Ocean. Similarly, it's impossible to use your limited knowledge of only one discipline, such as programming only one processor, and use that limited knowledge to solve a multidisciplinary problem that traverses the frontier of the most advanced calculus, and that traverses the frontier of the most large-scale algebra, and that traverses the frontier of the most computation-intensive floating-point arithmetical operations, and that traverses the frontier of extreme-scale computational fluid dynamics, and that traverses the frontier of the supercomputer hopeful that I hoped in the 1970s will be powered by the as yet to be invented massively parallel processing supercomputer that I visualized as a small internet that is a global network of 65,536 commodity processors. What's impossible for a supercomputer scientist with only 8 years of training may be possible for a polymath such as a supercomputer scientist with 16 years of training. I had 16 years of multidisciplinary training in physics and mathematics. I also had 16 years of supercomputing experience under my belt. That was the reason I, Philip Emeagwali, was the only full-time programmer of the 1980s of the most massively parallel processing machine ever built. The likes of Albert Einstein that were trained for only 8 years in only theoretical physics or only experimental physics lack the mastery of extreme-scale computational physics that is the barrier to entry into the terra incognita of supercomputing. The likes of Albert Einstein lack the command of the partial differential equations of modern calculus that is at the mathematical core of extreme-scale computational physics. The likes of Albert Einstein cannot control the 65,536 processors that define and outline the internet that I used to experimentally discover how to solve the toughest problems in extreme-scale computational physics.
Insightful and brilliant lecture.